Here we go. So the assignment is to read about Kirchhoff's voltage law. It tells you a little bit about the person. I've summarized it as in the most important part here. And your assignment is to find page 16. All the pages are numbered. They're handwritten at the bottom of each page. I'll be showing you page 16 in just a minute, and we'll actually be practicing one or two of them. Next, you're going to read about Kirchhoff's junction law. I think I have that spelled wrong. There's two F's in Kirchhoff. Sorry about that. I got it right in the title, but not in the subsequent. And the current law is even easier than the voltage law. And we're going to introduce kind of the formal notes on series circuits and compound circuits today. So without further ado, let's kind of dig into, here it is, into Kirchhoff's voltage law. And so, here we go. So this is page 15, as you can see, and we are going to be examining, let's kind of minimize this down. There we go. We're going to be taking a look at how voltage works in circuits. Quite honestly, you actually already know this. If you've watched any of my previous videos, we talked about a really important idea about energy. And voltage is not the same as energy, but the idea here is that starting at batteries do this, basically give the charges that are in the circuit different amounts of potential energy, electrical potential energy. And as the current flows through a circuit from the battery, it can go through a straight path, it can go through a branched path, or any combination. But every time it hits a load can be a bulb, a resistor, a motor. Every single device that you plug into a circuit along those lines, that there is some voltage loss. So you basically have your maximum voltage coming out of the battery. We could say the voltage from A to H is actually the voltage of the battery. And then when it goes through BC or C to B, depending on which probe you put on which side, black or red, you're going to find out that this is a negative voltage, right? Some of us learned that if you make it positive or negative, but if you subtract the voltage drop from C to B, from the V of the battery, and you subtract the voltage drop at D to E or E to D from the battery, and you subtract the voltage here, the total voltage, right? The voltage total for the loop, for the closed circuit, is equal to 0 volts. That is to say, the total energy that the battery provides, the potential energy provides because of the electric field that it sets up, all of that energy has to go somewhere. So all of these drops, which are negative, basically take away any of your positive voltage that's coming from the battery. So this page is kind of showing you, if you have only one item in the load, then your V of your battery minus your V from B to A better be 0. The path of the current is flowing this way if we're talking about traditional current, because it always comes from the positive side of the battery. Remember, the electrons actually go the other way. This is the same circuit, just drawn with a resistor instead of a instead of a light bulb. But I'm not so much worried about Kirchhoff's voltage law in terms of you being able to write out the full equations. As long as you get the idea that all of the energy dropped across each resistor has to add up to the total because of conservation of energy, and you never send energy back to the battery unless there's a short circuit. So kind of Kirchhoff's voltage law. You are challenged to do something a little bit different with it. Part of your homework today, let me go to the next page, is to calculate, and somehow I've already got some stuff on the page, is to calculate the voltage drop at each resistor. And this is not truly part of Kirchhoff's law, but basically what it is that if you know the current and the resistance for that resistor, you know the current and the resistance for that resistor, you can use Ohm's law at each resistor. If you're writing this down, that's great. If not, I want you to, we're recording, so we'll post this right away and we'll get this up on Canvas so you can maybe review it later as you're doing your work. So page 16 is one of your first assignments, and it says calculate the individual voltage drops across each bulb and resistor. So let's make a list of all of our resistors. Let's make it resistors, their voltages, and their currents. And you're gonna see why I do this in this way. We're gonna call it an RVI table. So we have resistor 1 up here. Here's R1. It is an 8 ohm resistor. Its current is 2.0 amps. There's a reason why I left V in the middle. It has to do with a pattern you're gonna be using in the future. Then the second resistor, you do not need to write the KVL equations. I am not a big fan of those, writing out the individual voltage drops. I'd rather use this table system. That's what I have found students do best with. 4 ohms and 2 amps. And then finally 6 ohms, 6.0 and 2 amps. Now, I hope many of you noticed that in a series circuit, we haven't studied this yet, the current is the same all the way around, right? The current maintains itself at 2 amps as long as it never branches. So if you know Ohm's law is equal to V equals IR, that's one way to write it. You can either write I equals V over R. In this case, we're going to rearrange it. All you have to do, and you can do this in your head, I times R, 2 times 8, is 16 volts. I'll just change color for that. We're starting your homework together. You can actually kind of follow along if you want, or you can submit it later. Some people are doing it by hand. The second resistor, 4 times 2, 8 volts. And these are negative, right? These are the loss of energy. It's turning into light, it's turning into heat, but it is no longer electrical potential energy. And of course, 6 times 2, negative 12 volts. Do those add up to the voltage of the battery? And the answer is 16 plus 8, 24, plus another 20, plus another 12 is 36 volts. So negative 36 volts added to the V of the battery has to equal 0. So we know that these are all correct. Now, sometimes we just drop the negative signs. We say that's 16 volts of delta V as opposed to negative 16. It's just kind of a convention we get into the habit of doing. Okay, can you find the individual voltage drop against each of these resistors in the second one? I'm going to leave this up to you. You're going to find the voltage drop for R1, for R2, for R3, for R4, and for R5. You could use the table I recommend, but you do not need to use, again, this equation. That's another teacher's preferred way of doing it. Oh, we forgot to do the top one example. I guess we could have done that one. So if you can do both the top and the bottom one, making your own RVI table, that would be superb. So Kirchhoff's voltage law, as well as how to apply voltage to each of these junctions. Next slide. Kirchhoff's junction law, much easier. Well, not easier. I just think more straightforward. It's not hard to add up voltages, but this one conceptually makes a little more sense. I don't know if any of you have been kayaking, or if any of you have ever, we got someone joining our class. I'm gonna let them in, sorry. You've ever been in a canoe, and in rivers of New Hampshire and Maine, up on the Kennebec River, they measure the flow rate of the river because the river is controlled by hydroelectric dams. So someone in the power company can determine how much energy is flowing through a dam every hour or every minute or even every second. So let's pretend this is river water, and let's say 10,000 gallons. Sounds like a reasonable number. Well, if 10,000 gallons are flowing every second, this is a pretty big river, going into a junction. So here it comes out of the hydroelectric dam. They've got a flow rate meter on it. Well, here comes the Kennebec River, and it's going to meet a fork. Actually, the Kennebec River isn't known for forking. Maybe it goes around an island. It doesn't really split into many sub-branches, but nonetheless, it's reached what we call a node. Well, these two branches, branch 1 and branch 2, they look pretty equal to each other. So a lot of people intuitively say, oh, when current reaches a junction, it always splits in half. And there is no rule that says that the current has to split equally. What it says is that the I total before the current splits has to be equal to I1 plus I2. What if one part of the river, after it splits, is really wide and one part's really narrow? The current is not going to be the same. But we do know that the total amount of water flowing per second is going to be equal to in the two parts, is going to be equal to that from before this junction. So visually, I want you to be able to see and do a puzzle that kind of has to do with junctions. So let's come down here and let's try to write an equation that describes how current flows in this circuit. So I kind of, for efficiency and since we're recording, I'm going to help you hopefully notice that I2 and I4 are both going in. This is a more complex situation. This is not just a one goes in, two comes out situation. Do you notice that I2 and I4 are both going in? So if you were to add up I2 plus I4, the total current going into the junction, into the node, and let's switch, well, it must be equal to I1 plus I3. Lowercase i's are not commonly used for current, but they are for, on that visual that I found. So the two coming in added up have to be equal to the two coming out. Again, this is a page that you're being assigned to do. It's not too bad, but let's do maybe one more together. Let's actually try maybe a more challenging one. How would you write this? Well, essentially what we have is we have current from before R1, here's 2, here's 3, here's 4, and here's 5. So those are the pathways or the resistors that are going in. So what we know is that the current that goes into the junction, I total through R1, what would happen to the current? Well, it's going to get split so that R2, R3, and R4 get some, but, oops, let's clean that up. I don't mean to write R. I mean to write I2 plus I3 plus I4. And then on the other side, do you notice that I5? So these three are additive and they have to add up to the current because there was a node before they split. And then after they split, they come back together. So current simply adds up and can be divided 2 ways, 3 ways, or many more ways. So I'm going to let you write the I equations for each of those on page 17. And we only have a little bit of time today. This is a little different. Usually you don't hear me lecture. This is more like we watch in the video before, but now you won't have to watch another video. So let's pop ahead one more slide to finish our kind of our notes for today. So finally, we get to something that seems like we should have, some of us have known about for a while, something called a series circuit. They're the most basic kind of circuits, I guess, that we will face. Some teachers teach that there's something called a simple circuit, which has just one battery, one resistor, and it goes back to the battery. And that, by definition, I guess, isn't series because there's only one resistor. This diagram, these are created by Mr. Wadman. He's a great artist. He came up with this bucket man. So bucket man sometimes carries a bucket on his head. Sometimes he's carrying two on his shoulder, on his arms. But what this represents is we have an energy supply, right? We have a source of potential energy in the battery. Here are the electrons carrying energy. This is a representative of an electron carrying energy. Well, why do they have energy? Well, because of their position in the electric field created by the battery. And the battery, of course, has a positive and negative terminal. So what you notice is that they're full of energy as they start marching down the path. And what they do is they lose some of their energy going through the resistor. And you notice that they literally now only have one bucket. The other one's on their hip, or they're just running now. And then they follow along. But do you notice that they never lose energy? They carry less energy, but they never lose energy while they're in the wire. So this little cartoon is a great way of remembering this. And the second time they go through a resistor, there's going to be a delta V, and now they come back energyless or bucketless. So you have all the skills to kind of pull this together. And let's kind of examine series circuits. So The key characteristics is that there's one path, there are no nodes or no branches, okay? There can be one or more batteries represented here, and the key ideas are, according to the Kirchhoff's voltage or loop rule, that the voltage drop at R1 plus the voltage drop at V2, at R2, excuse me, has to add up to the total of the battery. We've examined that in lab and now through the video. The current, because there's only one pathway, look at this equation. Basically, it's an equality statement. It's not truly an equation. It basically reminds you that whatever your current is here, I total here, it's going to be the same current here, and it's going to be the same current there. There's no split. And lastly, something you also discovered in lab is that resistance is simply additive. You add up all of your resistors, 1 plus 2 plus 3 plus 4. This formula, let's put a dot, dot, dot on it. You can keep adding. It's just arithmetic. So your last part of the assignment, and this is kind of good timing, is I would like you to complete this analysis table. And let me explain briefly what it is. It's, we call them an RVI table. Now you might see why I used RVI tables before. RVI tables basically are the beginning of circuit analysis. And circuit analysis says, without using a multimeter, without using real life circuits, can you predict what's going to happen in a circuit? And here's step one. Step one is to look at all of your resistors and classify what kind of circuit is it. And because there's only one pathway and they never branch, it's a series circuit. So if someone said, find the total resistance or the equivalent resistance for the circuit, you would look around your circuit and go 12 plus 4 plus 6, or a total of R total of 22 ohms. Now, that doesn't relate to the next problem. I'll show you what to do, but that's how easy it is to start. Step two.
Mr. Hausman?
Yes.
They just closed school for the rest of the year.
Yeah, I can't really focus right now.
Like closed school for
like Charlie Baker said, no school.
For the school year, not all of 2020.
Through the end of the year, yeah.
The end of the school year. Do you mean as in like there's no lessons going on, or just mean that we're not going back into our building? Do you know?
Building,
it's a
I think.
building. Okay. I kind of knew that was coming. I'm not saying I have inside information, but if you look around at the data, so sorry if that is a huge distraction. It happened during our lesson. That's okay. I also am like hitting up on the timeline when you have to head to your next class. We're not quite done. Take a minute if that's angering you, if that's upsetting you. Certainly, that's way more important than learning about circuits. But for the people who can stay focused, like I'm with you. I think that was Katie who called it out. I think others were giving me information. That's great. So it sounds weird. I just want to finish because sort of a mid-recording, but thank you for sharing. Is that, and you're like, you're so cold. I'm not. I just want to maybe allow some people who do want to finish. Let's do a whole problem together. The total resistance of 2 plus 4 plus 1 is 7 ohms of resistance. You do not need to show that work if you can do addition in your head. The voltage total is 14. So how would you find the total current right here? You would use Ohm's law, 14 over 7. And that means there would be 2 amps. And I know I'm kind of rushing this. As soon as you have this step done first, and then this step done second, where you use the V total and the R total to find the I, right, of 2 amperes, the current for every single resistor in that pathway, you now know. This only works for series circuits, but there's only one current, 2 amps, 2 amps, 2 amps. Now, does anyone notice that it's just like what we taught about 2 pages ago? V equals IR. It's a little bit like Sudoku. I times R, because that's the other way to write Ohm's law, and equals 2 times 2, or 4 volts. 2 times 4 is 8 volts. 2 times 1 must be 2 volts. And look really carefully at the coincidence. It's not a coincidence. It's just how circuits kind of come together. 4 plus 8 is 12 plus 2. and it matches the voltage total of your battery. So I'm going to save this. I'm going to hit stop. We didn't have a lot